Everybody, in this video, part 3 of the Manifold series, we're going to be talking about orientation on a manifold. And so the aim of this video is to introduce two different definitions for orientation on a manifold and show that they are equivalent. And then I'm going to make a follow-up video to this just because I feel like the last two videos have been kind of long, so I'm going to split it up. So this one's just going to be introducing the definitions and showing their equivalent, and then the next one will be showing certain spaces are orientable and giving examples of non-orientable manifolds. So first of all, a manifold can be presented as is a space on its own and its selection of charts, which by the way is called an atlas. Atlas is a collection of charts, and remember, charts are the open regions which are identifiable with Rn, right? And so for a given manifold, right, there are different ways we can basically put coordinates, right? This is essentially putting coordinates on the manifold and then specifying how the coordinates are related on the overlap of the charts, right? Because like think for example with the sphere, right, we can pick 2 points, right, as like the North and South Pole, and define charts as everywhere except the North Pole and then everywhere except the South Pole. But you know, we could pick any two points, right? It doesn't matter whether they're antipodal. We could pick, you know, this point and this point. It doesn't matter. And so the point is here, whether essentially you want to call a manifold orientable, which basically means there is an atlas which gives M an orientation. And so if M has an atlas, or if M has an orientation which is specific to its given atlas, then it is oriented. So I just want to point out the difference between the two words orientable and oriented when we're talking about manifolds. So our first definition is going to be M is oriented, and remember this is specific to the atlas, or the coordinates on M. Hello? Okay, there we go. Atlas. If on non-empty overlaps of charts, so if this is non-empty, then the determinant of the transition, which again looks like this, so this is a Jacobian of the transition functions, is positive everywhere on this region. And remember, we specified that in the definition of a manifold, this is always going to be non-zero, right? And since it is since it has a continuous dependence on the overlap, right? So let's say we had 2 regions here, UP and UQ, right? since this Jacobian is going to be continuous and it can't be 0, basically on each overlap it will either be positive or negative. And so for M to be oriented, we're saying that it's always going to be positive no matter what overlap we look at. The Jacobian in that overlap will be positive. So that's definition 1. So let's give an example. Euclidean space is oriented, where we take as its atlas, really we only need one chart. So one chart, which is just all of Rn, right? Because the idea of a manifold is that we're piecing together Euclidean space, but if we just start with Euclidean space, there's nothing to piece together. So we just have one chart here, and since we have one chart, there are essentially no overlaps to worry about. So this means that it is oriented, sort of in a trivial sense. And furthermore, we can essentially show that, right? Consider, say, like, if we have our typical rectangular coordinates, right? This defines an orientation. But now let's say instead, let's say we said the y direction, the positive y direction was like this, right? So this would be 1 and this would be -1 for the y instead of 1 and -1 here. This would be an opposite orientation to this one. Opposite. So there are two orientations on Rn. And in general, if a manifold is connected and orientable, this implies two orientations. And so Euclidean space is definitely connected. Remember, we're using path connected instead of general connectedness, but Rn is connected anyway. But remember, connected just means we can connect any 2 points by a path, which we certainly can do in Euclidean space. And it's orientable. We've already shown it's orientable. So that means there are only two orientations, which we can basically say a positive and a negative orientation. All right, now let's look at the next definition. And for this definition, we have to define, we basically have to look at the tangent space of a manifold. And we haven't talked about this in too much detail, but I'm just going to use the sphere as an example. Actually, I'll use the circle. This will be easier for me to demonstrate. So imagine we have the circle S1. This is a manifold given by piecing together R, right? We can consider, the north and south pole stereographic projection coordinates. So this is a manifold. And so at each point, there is a tangent space, which we can consider basically being inherited from its local coordinates, right? So at this point, right, at a point in S1, locally, this looks like the real plane, right? If we have this point X, if we zoom in, it looks like R. And R has a tangent space, right? We have 2 directions to go in, right? So we basically just have dx, right? So the tangent space is a one-dimensional vector space spanned by dx. Similarly, if we were dealing with the sphere, delete that. Okay. And if we looked at a point, right, this is S2, locally, this point, around this point is going to look like R2, and R2 has a tangent space given by dx and dy. So it's a two-dimensional vector space spanned by dx and dy, which are the local coordinates. And really here I should say dx1 and dx2. So these are the local coordinates for x on the manifold, because around x we can consider the manifold to just being Euclidean space. And Euclidean space, we know what its tangent space looks like. So I'll go into more detail about that in a later video, but we need that information for now. And so basically, at a point x in M, there is a frame space so a frame tau is an ordered basis for the tangent space which we denote as txm. So remember, the tangent space is a vector space. So here we're using the idea of a basis of a vector space. And so we have a standard basis given by the differential of the coordinates. But of course, a vector space can have any amount of bases. And so essentially any two bases, or well, I should say frames now, any two frames, tau 1, tau 2, are connected by a linear transformation let's call it just A. So in other words, like A tau 1 equals tau 2. If the determinant of A is greater than 0, then tau 1 and tau 2 have the same orientation class. And we know that basically we're assuming, since these are bases, the determinant of A will not be 0, so this will never be 0. So it's either going to be positive or negative. So if it's negative, so negative implies different classes. Okay, so here we've defined the frame space at a point. So we have different bases for the tangent space, and given one of these, or basically we can take two bases and say, okay, they either have the same orientation class or they have different orientation classes. So now an orientation on M is a continuous choice of orientation class at each point in M. So at each point in M, we're saying, okay, the orientation class of the tangent space is, let's say the one that aligns with the standard dx dy, right? Or it could be the opposite. So basically, at each point, there's two choices, and so we just have a continuous choice. And the continuity means that at each point, we can find some neighborhood where all of the orientation classes within this neighborhood are going to be the same orientation class. And so if we can't pick an orientation in this manner, this means it's non-orientable. So now let's show that the two definitions are equal. So let's go 1 implies 2. So 1 is saying that, okay, we know that on each overlap, the determinant of the Jacobian is positive on every overlap. So what we're going to do is at each x and m, choose the orientation class given by Rn. So essentially what we're saying here is that we're taking tau, our ordered basis, to be dx1 ... dxn, right? So the orientation class is the orientation class which agrees with this tau. So in other words, if any frame such that the transformation between that frame and this one has a positive determinant. So clearly this is going to be a continuous choice, right? Because M is just Rn patched together. If there is an overlap, so if we have a point X in an overlap, right, there's two possible coordinate systems, and so there's two possible inherited orientation classes, right? We could have dx1 p ... dxn p, or we could have dxq1 ... dxqn, right? We could have the frame coming from UP, or we could have the frame coming from UQ. But in either case, since we know that the transformation between XP and XQ is positive, there's a positive Jacobian, then this Jacobian is just going to be the A that transforms this frame into this frame. And so we know that these two frames have the same orientation class. And so this choice is consistent on the overlaps. And so that implies that we can indeed use this choice of orientation class. It's consistent on overlaps, and it continuously depends on X. Next, we go 2 implies 1. So in this case, we have an orientation class at each X and M. And so what this means is that so what we're going to do is say at each X, pick a frame tau which belongs to this orientation class. So I'm just shortening that as O class. And now what we're going to do is define local coordinates x sub I, let's just say x tau, such that tau, this frame, is dx1 tau ... dxn tau. So we're using this frame to define coordinates near x, right? So x is some point. It has it has some tangent space, and what we're saying is that the tangent space, we have an ordered basis for it, which is given by tau. That's the frame, the ordered basis, and we're using that basis to define coordinates around x. Right? And so now, so this creates an atlas on M, right? We have a collection of open regions around each point that is identifiable with Rn. And so now we want to show that on overlap regions, so let's say we have overlap regions, we want to show that the Jacobian of the transformation is, or the transition function is positive. But on this overlap, right, we know that x has some orientation class, right? That's what we're starting with. That was our assumption, is that at every point we have some orientation class. And so the frames dx, the frames inherited from one region and the frames inherited from another region must be in the same class. In other words, that means that the transformation from this frame to that frame has a positive determinant. But we know that this transformation is just the transition function. So we know, so this implies that this Jacobian is positive. So hopefully these proofs make sense. I tried to be as, visual as possible. And again, this is the first time I've done upper level math on this channel, so hopefully this format works for everybody. So in the next video, we're going to be going over some more spaces. And yeah, so I hope to see you in that video.